Alright, let's go. Number 8. The CMB Cold Spot Search. In the early 2010s, Ranga Ramchari sat at NASA's Jet Propulsion Laboratory in Pasadena working through data from the Planck satellite on what most astronomers would call the unglamorous end of cosmology. His job was foreground subtraction, take the cosmic microwave background, remove the known contamination from Milky Way dust and distant galaxies, hand the collaboration a clean residual map. He was, essentially, cleaning up. The cosmic microwave background is the afterglow of the Big Bang, released roughly 380,000 years after the universe began. Standard cosmology predicts it should be smoothed to about 1 part in 100,000 across the entire sky. Tiny variations reflect the quantum fluctuations that eventually seeded galaxies. Once you subtract dust, gas, and known point sources, what remains should be, in cosmological terms, statistical noise. What remained was not statistical noise. In specific patches, the residual flux came in roughly 4,500 times brighter than the model predicted. Not diffuse. Not uniform. Structured, Sherry stared at the numbers and asked what physical process could possibly produce them. His paper appeared in the Astrophysical Journal in September 2015 under the title Spectral Variations of the Sky: Constraints on Alternate Universes. In it, Sherry cautiously proposed that the excess could be consistent with a bruise, a collision signature. From the very early moments after the Big Bang, when our nascent universe may have grazed against a neighboring bubble universe expanding out of the same quantum foam. Milky Way dust was the obvious first suspect. Spectral analysis ruled it out. Instrumental artifacts from the Planck detectors were audited exhaustively and could not produce a pattern of that magnitude. Contamination from unresolved background galaxies was modeled and could account for a slice of the excess, not the whole. A rival explanation, a colossal supervoid distorting light through the integrated Sachs-Wolfe effect, was proposed by Istvan Saputi's group at the University of Hawaii in the monthly notices of the Royal Astronomical Society in 2015. It matched some features. It could not reproduce the temperature depth, and the collision hypothesis itself sat at roughly 2.5 sigma of statistical significance, respectable enough to publish, nowhere near the 5 sigma bar physics requires for confirmed detection. The cold spot lies in the constellation Eridanus, low on the southern horizon in December. It is visible in the sense that its coordinates map onto a specific patch of sky you can point a finger at from any dark beach south of the equator. If you have ever looked at that stretch of sky, you may have been looking at another universe pressed briefly against ours. If a bruise left in the light of the Big Bang does not count as evidence, what would? The next experiment took the same premise and ran it through a completely different satellite. Alright, number 7. The Eternal Inflation Bubble Collision Search. Stephen Feeney was a graduate student at University College London in 2010, working under the cosmologist Hiranya Paris on a broader statistical audit of the DOMAP satellite data. The multiverse question came up almost as a side project. Could you, in principle, build a mathematical template of what a scar from a collision with a neighboring universe would look like, and then search a real dataset for that template? The theory of eternal inflation, developed largely by Andre Linde at Stanford and Alexander Vilenkin at Tufts University in the 1980s, predicts that inflation never entirely stops. It continues in a vast background, spawning an endless number of pocket universes as separate bubbles. Standard predictions say most bubbles should have been driven apart by inflation faster than any two could ever come into contact, but some models allow, occasionally, for a graze. A graze, if it happened in the first fraction of a second after our bubble formed, would leave a specific imprint on the CMB, a circular temperature discontinuity, cold in the center, with a sharp ring around the edge. Feeney and his collaborators built the template. Then they went looking. The paper appeared in Physical Review Letters in July 2011, authored by Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris, under the title First Observational Tests of Eternal Inflation. They identified 4 candidate circular features in MAP 7-year data with statistical significance above chance. 4 scars. 4 potential collision points with 4 different neighboring universes. Follow-up analyses using the higher-resolution Planck satellite data, published by the same group and by others between 2013 and 2015, drained the confidence out of every candidate. 3 of the 4 features weakened or vanished under sharper resolution. The remaining one hovered near the noise floor. Alternative explanations, cosmic string signatures, primordial magnetic field imprints, foreground contamination from cold gas clouds could each account for some of the anomalies. And crucially, the look elsewhere effect, which corrects for the fact that random noise in a large enough dataset will always produce a few striking-looking coincidences, ate most of the remaining significance. The 4 candidate patches Feeney identified are still up there. They are still technically in the data. Every time the Planck team releases a new reprocessing of the CMB, someone in the collaboration has to decide whether those 4 patches are worth looking at again. So far, the answer has been, probably not. How many statistical ghosts does a search have to produce before the search itself is what needs re-examining. The next attempt to find another universe abandoned satellites entirely and looked for something even harder, a leak. Alright, number 6. The LHC search for extra-dimensional leakage. Nima Arcani-Hamed at Berkeley, Savas Dimopoulos at Stanford, and Gia Diwali at NU were not trying to find parallel universes in the late 1990s. They were trying to solve a much smaller problem, why gravity is so absurdly weaker than the other 3 fundamental forces. Their proposed answer, published in Physics Letters B in 1998, was that gravity might not actually be weaker at all. It might just be leaking somewhere the other forces cannot follow. In their model, and in a related model by Lisa Randall at Harvard and Raman Sundram at Johns Hopkins published in 1999, extra spatial dimensions exist beyond the 3 we experience, but they are curled up small, or hidden in ways that only gravity can access. If the model is correct, then when protons collide with sufficient energy at a particle accelerator, some fraction of the collision energy should vanish into these dimensions and register in the detector as missing. When the Large Hadron Collider came online outside Geneva in 2010, the ATLAS and CMS detector collaborations began looking specifically for that missing energy signature. They ran the search across every collision energy the machine could reach. Between 2011 and 2023, ATLAS and CMS published more than a dozen dedicated searches for extra-dimensional gravity signatures, testing everything from mini black hole production to graviton emission to Kaluza-Klein tower excitations. The most sensitive analyses ruled out large extra dimensions at scales below roughly 4 to 6 trillion electron volts, depending on the specific model. Beyond that, no significant excess of missing energy events was found in any collision channel. Standard model background processes, particularly neutrino production in weak decays, accounted for essentially all observed missing energy events. Higher energy runs increased sensitivity but produced no anomaly. Alternative extra-dimension models with different geometries were tested and constrained further. Warped Randall-Sundram scenarios, flat-add scenarios, universal extra dimensions, each fell below the threshold where the LHC could see them, if they exist at all. Even the mini black hole production, predicted by some variants, which would have been an unambiguous signature of gravity leaking into extra dimensions, produced 0 confirmed candidates in over a decade of collisions. If extra dimensions exist and gravity is leaking into them, that leak has to be happening at energies our largest machine cannot reach. The next accelerator that could push past the current bound does not exist yet, and its construction is not funded. The question is, in practical terms, on hold. What happens to a physical theory when the only way to test it is to build a machine no civilization has yet chosen to build? The next experiment did not look through a telescope or a collider. It looked at the same slit of light over and over for 70 years. Alright, number 5. The double slit interpretation tests. Hugh Everett III was 24 years old and finishing his doctoral thesis under John Wheeler at Princeton in 1955. He was trying to resolve what everyone in the field called the measurement problem, the awkward fact that quantum mechanics predicts particles exist in superposition until measured, then abruptly collapse into a single outcome. Everett proposed a radically simpler solution. He removed the collapse. His 1957 paper in Reviews of Modern Physics, titled Relative State Formulation of Quantum Mechanics, argued that the wave function never collapses at all. Instead, every possible outcome of every quantum measurement actually occurs, in a separate, non-interacting branch of reality. The observer branches along with the outcome. The universe splits, quietly and continuously, an astronomical number of times per second. Wheeler tried to soften the interpretation for the physics establishment. It landed badly. Everett left academic physics for defense work at the Pentagon. His idea sat mostly dormant until Bryce DeWitt revived it in the 1970s under the more evocative name Many Worlds. Direct tests of the branching claim are, by construction, impossible. The branches do not communicate. But experimentalists have spent decades running increasingly precise double-slit and delayed choice experiments specifically to constrain which interpretations of quantum mechanics remain viable. The delayed choice quantum eraser experiment, formalized by Marlon Scully and Kai Doctrell in Physical Review A in 1982, and executed by Yoon Ho Kim and collaborators in 2000, tested whether measurement outcomes could be retroactively influenced by observation decisions made after the particle had already passed through the slits. The results consistently favored the quantum predictions over every classical interpretation, but they did not distinguish Many Worlds from its main competitors, the Copenhagen interpretation, decoherence-based interpretations, pilot wave theory as developed by David Bohm in 1952, or the more recent cubism framework of Christopher Fuchs and Erdiger Schack. Each interpretation reproduces every experimental result to date. The Nobel Prize awarded to Alan Aspect, John Clauser, and Anton Zeilinger in 2022 for their tests of Bell inequalities ruled out local hidden variable theories, but did not rule out Many Worlds, and did not rule it in. If Everett was right, then every choice you failed to make, every job you did not take, every argument you walked away from, every version of your life that was possible but did not happen, exists in a branch of reality separated from yours by a distance no measurement can cross. Or none of it exists. Nothing in 70 years of experiment can tell you which. What kind of scientific claim is one whose truth cannot, in principle, ever be verified by anyone? The next search moved from single photons to entire colliding black holes and asked whether they echo. Alright, number 4. The Gravitational-Wave Echo Search. By late 2016, Jeheda Bedi was a graduate student at the Perimeter Institute in Waterloo, working with the cosmologist Nyayesh Afshordi. LIGO, the Laser Interferometer Gravitational Wave Observatory, had confirmed its first black hole merger the year before. Abedi and Afshordi were combing through the public LIGO data for something the collaboration's own analysis pipeline had not been designed to find: faint, repeating structure after the main gravitational wave signal ended. General relativity, as formulated by Einstein in 1915 and refined by countless researchers since, predicts that when two black holes merge, the resulting event horizon should ring down, emit a decaying sequence of gravitational waves, and then go silent. Nothing else should follow. The horizon is, in the classical theory, a perfect one-way membrane. Anything inside it or anything happening at its surface is inaccessible to outside observers. Some theoretical models predict otherwise. String-theoretic fuzzball proposals, firewall arguments, models involving extra dimensions or quantum gravitational modifications near the horizon, each predicts that faint echoes should follow the ringdown. If those echoes exist, they would carry information about a structure at the black hole's edge that classical general relativity forbids. In December 2016, Abedi, Descartes, and Afshordi posted a preprint titled Echoes from the Abyss, Evidence for Planck Scale Structure at Black Hole Horizons. They analyzed LIGO data from the first 3 confirmed mergers, GW150914, GW15126, and GW151112, and reported evidence of repeating echoes at a statistical significance of roughly 2.9 sigma. Not a discovery. Suggestive, the LIGO scientific collaboration ran its own analysis using its full suite of signal processing tools and could not reproduce the significance level. An independent group led by Julian Westerwek at the University of Cardiff reanalyzed the same data with different template banks and found the echo signal weakened toward the noise floor. Instrumental glitches in the LIGO detectors were investigated as potential false positives and could not be entirely ruled out as contributors. A 2018 follow-up by Abedi and Afshorty using data from the neutron star merger GW170817 reported an even higher significance echo, 42 sigma, but again, independent reanalysis could not confirm it. As of the most recent LIGO Virgo Cagra observing runs, no echo has been detected at unambiguous significance, if echoes exist. They suggest that the event horizon is not the smooth wall Einstein described. Something is out there, at the edge of every black hole in the sky, that is not supposed to be there. And if the something is what some of the models predict, a structure connecting to another region of space-time, the sky is full of doors. How many black hole mergers do we have to listen to before absence of echo becomes evidence of absence? The next experiment abandoned instruments entirely and lived inside a thought. Alright, number 3, the quantum suicide experiment. Max Tegmark was a young cosmologist at the Institute for Advanced Study in Princeton in the mid-1990s. He had become convinced that Everett's many worlds framework was not just viable, but likely correct. He wanted a way, a thought experiment, not an actual experiment, to illustrate what it would mean for a single observer to, in principle, verify the interpretation from the inside. In standard quantum mechanics, a particle in superposition has a probability distribution over its possible states. When measured, one state is realized and the others vanish. In the many worlds interpretation, every state is realized, in separate branches. The observer's experience follows one branch, but the observer in every other branch also continues to exist, having their own experience, in their own branch. Tegmark's thought experiment ran as follows. Place a physicist in front of a gun triggered by a quantum measurement. If the measurement returns spin up, the gun fires. If spin down, it clicks harmless. Standard quantum mechanics predicts a 50% chance of survival per trial. Many Worlds predicts that in half the branches, the physicist dies, and in the other half, continues. Tegmark formalized the argument in a widely cited paper titled The Interpretation of Quantum Mechanics, Many Worlds or Many Words, published in Fortschritt der Physik in 1998. The claim was mathematical. If Many Worlds is correct, an observer running enough trials will always find themselves in a branch where they survived, no matter how improbable that survival becomes. The probability of your continued subjective experience, from your own vantage point, approaches 1. The experiment cannot be run. Even if a physicist were willing to conduct it, no confirmation is possible. The successful observer cannot communicate their survival to anyone outside their branch, because the observers in the other branches, from their perspective, watch them die. Skeptical philosophers, notably David Lewis and later David Wallace at Oxford, argued that the reasoning confuses subjective survival with objective probability in ways that may not be coherent. Bruno Marchall's earlier work on the quantum immortality version of the argument in the 1980s attracted similar critiques, and the entire framework depends on Many Worlds being correct, which, per the previous entry, remains untestable. If Many Worlds is right, and if the quantum suicide logic holds, then you have already survived every event in your life that could have killed you. Every near miss, every close call, every time the car did not quite hit. Somewhere in the branching structure, in most branches, it did. What kind of experiment is one whose only successful outcome is one you cannot report? The next search returned to physical instruments and looked for the fingerprint of the multiverse inside a single hypothetical particle. Alright, number 2. The Axion search for landscape evidence. Roberto Peche and Helen Quinn at Stanford were trying to fix a technical problem in the strong nuclear force in 1977. Their proposed mechanism predicted a new particle, which Frank Wilczek and Steven Weinberg independently named the Axion in 1978. It was supposed to be a small fix to a narrow puzzle. It became something much larger. Over the following decades, cosmologists realized that axions, if they exist, would have been produced in enormous quantities in the early universe, and would plausibly account for some or all of the dark matter that makes up roughly 85% of all matter in the cosmos. Meanwhile, string theorists working on what became known as the landscape model, a framework popularized by Leonard Susskind of Stanford in his 2005 book The Cosmic Landscape, proposed that the fundamental constants of physics could vary across an enormous number of parallel universes, each governed by a different vacuum state. The specific mass of the axion, if measured, could distinguish between different landscape models. A very light axion in the microelectron-volt range would be consistent with certain string-theoretic vacua. A heavier one, in the millielectron-volt range, would favor others. The axion's mass is, in this framework, a fingerprint, indirect but potentially decisive. The Axion Dark Matter Experiment, or ADMX, has been operating at the University of Washington in Seattle since the mid-1990s. It uses a cold, tunable microwave cavity inside a strong magnetic field to try to convert axions from the surrounding dark matter halo into detectable photons. Over roughly 3 decades of operation, ADMX has scanned frequency ranges corresponding to axion masses between about 2 and 5 microelectronvolts, ruling out a specific range of axion coupling strengths at each mass. Newer experiments, Haystack at Yale, CAP in South Korea, Oregon in Australia, extend the search to higher masses. No axion has been detected. The searches have set increasingly tight upper limits on how strongly axions can couple to photons if they exist at the masses tested. Alternative dark matter candidates, weakly interacting massive particles, sought by direct detection experiments including Echinonant in Italy and LUX Zeppelin in South Dakota, have similarly produced no confirmed signal despite decades of increasingly sensitive searches. And even if an axion is eventually detected, the connection to the landscape multiverse is theoretical, not automatic. A measured axion mass would constrain, but not uniquely identify, which vacuum our universe lives in. The dark matter that gravitationally shapes every galaxy you can see, including the arms of the Milky Way holding your solar system in place, may be composed of particles whose properties encode information about the specific universe you happen to inhabit. Or it may not. Nothing in 3 decades of experiment has settled the question. If a particle you cannot detect turns out to hold the address of your universe, what would it take to read the address? And the last item on this list is not really an experiment at all. It is an argument. Alright, number 1, the fine-tuning argument. The observation that many of physics' fundamental constants appear precisely tuned for the existence of complex structure, atoms, chemistry, stars. Life dates back at least to Fred Hoyle's work in the 1950s on the carbon-12 resonance level, which he correctly predicted must exist for stellar nucleosynthesis to produce enough carbon to make organic chemistry possible. Over the following decades, physicists cataloged dozens of similar coincidences. The fine structure constant, which governs the strength of the electromagnetic force, has a value of roughly 1 over 137.036. If it were a few percent larger, stars could not fuse elements past helium. A few percent smaller, and stable atoms could not form. The cosmological constant, the energy density of empty space, is measured at roughly 10 to the negative 122 in Planck units, a value so improbably small that if it were larger by a factor consistent with basic theoretical expectation, no galaxies would ever have formed. And there are more like it. Many more. There are 3 main positions on why. The first is chance. The constants happen to have these values, and we happen to exist because they do. The second is design. Some external agent chose the values. The third, developed most influentially by Leonard Susskind in the string theory landscape framework, is that the constants take every possible value across an enormous ensemble of universes, and we necessarily observe values compatible with our existence because we could not exist to observe any others. Susskind's book, The Cosmic Landscape, String Theory and the Illusion of Intelligent Design. published in 2005, argued that the string theory landscape naturally produces on the order of 10 to the 500 distinct possible vacua, a number so large it exceeds the number of atoms in the observable universe by more than 400 orders of magnitude. Later refinements by Michael Douglas at Stony Brook, Shamit Katru at Stanford, and others have put the estimated count in an even larger range, though the exact figure depends on theoretical assumptions no experiment can currently constrain. The chance explanation requires an extraordinary coincidence with no underlying cause, which most physicists find unsatisfying but not disprovable. The design explanation sits outside science, since it invokes an agent whose existence cannot be tested. The landscape explanation is scientific in structure, it makes claims about physical reality, but the other universes it postulates are, by construction, causally disconnected from ours. No experiment run within our universe can detect them. Steven Weinberg's 1987 prediction that the cosmological constant should be small but non-zero, published in Physical Review Letters, was later vindicated when the constant was measured in 1998, and Weinberg's argument depended explicitly on multiverse reasoning. That success has been cited both as evidence for the landscape framework and as evidence for how far theoretical physics has drifted from its own falsifiability standards. The best current explanation for why you exist may be that you live in one of an unimaginably large number of universes, most of which contain no observers at all, and you observed this particular one because you could not observe any other. The alternative is that the constants of physics have their specific values for a reason no one has found in 80 years of looking. What kind of science is a science whose most successful predictions rely on entities its own methods forbid it to detect? Every experiment on this list sits at the center of well-tested physics, not the edges. The cold spot is in verified Planck data. Bubble collisions were formally searched in peer-reviewed papers. Extra dimensions have been hunted at the LHC for over a decade. Many worlds is a mainstream interpretation of the equations physicists use every day. None of this is fringe. This is the shape of modern cosmology when you follow its own logic to the places it does not want to go. The universe is not confused. We are, because our best theories keep pointing at doors we cannot open and cannot look away from. If you want to see more videos like this, click the video on screen now.